Hello everyone, I'm Frank and welcome to Frank Puzzles. And this is actually kind of exciting for me because I've never done one of these on this channel. I've done many of the Marty Sears Rat Runs puzzles, but this is the first time I'm doing a video on one of his Rat Run puzzles. And his Rat Run puzzles have always been super fun and super just the theme of them have been great. The logic behind them have always been really cool. So I hope you guys are in for a treat in this solve. It's an easy level puzzle, or it's rated easy by the people on the Logic Masters Germany forum. So take that easiness with a grain of salt. And on to today's puzzle, which is Rat Run 11, limited edition by Marty Sears. And as I said before, I'm a big fan of the Rat Run puzzles because they've always been super cool in theme, logic, everything, just the way it's constructed. Anyways, let's get to the puzzle. Let's get to the rules. Normal Sudoku rules apply, which means place the digits 1 through 9 once each in every row, column, and box. Aim of experiment. Finks the rat must reach. Finks is the protagonist in all the Rat Run puzzles. Finks the rat must reach the cupcake, which is here, by finding a path through the maze. The path, I can't speak right now. The path must not visit any cell more than once, cross itself, or pass through any thick maze walls. So, examples of thick maze walls, these are all thick maze walls here, right? And Fink starts off here, and then the cupcake is over here. So it has to find its way to here without entering a cell more than once, cannot cross itself either, and it cannot pass through any thick maze walls. As well as moving orthogonally, Finks may move diagonally if there is a 2x2 space in which to do so, but may never pass diagonally through a round wall spot or on the corner of a cell. So it cannot. So if Finks were here, he could not cross this way because we have a round wall spot on the corner of that cell, and that would pass through there. Obviously, he can't pass through here. Similarly, he can't pass through here or this way because that would be going through the round wall spot. And of course, he can't cross the wall. But if say Finks were here, he could cross this way diagonally because there is a 2x2 space where there is no wall in between and there's no round wall spot to block him. Okay. Teleports. Entering a teleport will cause Finks to be instantly transported to the matching colored teleport. From there, she can continue her journey. Matching teleports always have identical digits, but teleports that don't match always have different digits. So therefore, this is exactly the same digit as that. This is the same digit as that. This is the same digit as that. This is the same digit as that. And E is the same digit as that. And they all are different digits from each other. Okay. And as part of drawing her path, once she enters one of the teleportation areas, she teleports to the other one. Okay. Red current. A red current, actually current, I think is how it's pronounced. A red current always sits between an even digit and an odd digit. So as an example, if this were a 2, this would have to be a 1, a 3, a 5, a 7, or a 9 to basically maintain the odd-even parity between red currents. Test constraint. In this experiment, any cell on the path equals the digit at the top of its column plus the digit at the left-hand end of its row. Huh, interesting. So that means, for example, we know this is on the... Okay, so we know uh, we know that Finks herself is on the path. So what this cell equals, what's the digit in the cell must equal, it must equal the digit at the top of its column. So it would be equal to what this is, plus whatever this is. So this has to be the sum of these two cells, since it's on the path. We know the cupcake is also on the path. So this is also equal to the sum of this digit, or let's just make that one red. So this one will make yellow. That digit plus whatever that digit is, right? Because this has to be the sum of those two digits. Interesting. So any cell on the path has to follow this rule set, where it's equal to the sum of this digit plus the topmost cell in the column plus the leftmost cell in its row. Okay. And those are all the rules. If you'd like to play along, there's going to be a link in the description. And now, I'm going to get started. Let's go. Okay, so as we said, this has to be the sum of these two cells. So this is never a 9. So you can never have a 9 on the path. Actually, you can't have a 1 on the path either. Actually, well, no, 9 could be on the path. 1 can never be on a path. Okay, that's interesting. um, so the thing is, if it ever goes this way, it would have to teleport to there, right? But it could go enter this way and then enter that way, right? That is possible. We also know that so D has to be essentially blue, right? They're the same digit. We don't have to color those because that makes it confusing. We know C has to be one of these three, so one of those three is C. B cannot be here, obviously, or here. D can't be any of these. A can't be here, and A can't be here, so A is one of these three. A can't be here, and A can't be here, so it must be one of these four. Blue can't be here or here, so it has to be one of these four. Red can't be here or here, so it's one of these four. And we know red cannot be 9, because it must be the combination of that and this digit. So we know this has to be 1 through 8. And this has to be 1 through 8. Because this has to be the sum of those two cells. Similarly, this is 1 through 8. Not 0. 1 through 8. And this is 1 through 8. I don't know why I did that. So therefore, there's at least one row and one column where Finks cannot go through, right? Because we know one of these has to be 9 here, and one of these has to be 9. We just don't know which one it is, right? But wherever Finks goes, she eliminates 9s in every column in every row that she's in. So I guess it could be here, right? That could be the 9. That would be possible. Hmm. I realize I didn't define what orthogonal is, but it's not that. I mean, it's sort of implied, I guess. Anyways. B cannot be here either, or here. So B has to be one of these four also. B can't be here or here. That's fine. A can't be here. I don't know how helpful this is. Let's just clear out all the... Let's keep the time, and then clear everything out. We know these are 1 through 8. Hmm. So it could go something like that, right? And then go down to there. The shortest spaces are like these, and then the D, and then going down there. But for some reason, I mean, well, from my prior experience with the rat run puzzles, it's never that simple, right? Well, let's take a look. What happens if Finks goes that way, right? This is obviously the same value as that. Oh. Oh. Yeah, Finks can never touch any of these. Right? Because if okay, Finks can never get onto the column 1 or row 1. Why? Because that would then say that this if she was on essentially row column 1, that would say she was at E. If she goes to E, that means the cell on the path equals a digit at the top of its column plus the digit at the left hand. Well, the left hand is itself, but the top of the column has to be at least 1. So therefore, the path on the cell would have to be essentially itself, which is not possible. So therefore, Finks can never go on one of these cells because, again, if she goes to here, that value has to essentially be the leftmost, which is itself, plus another digit, which is obviously then would not be itself. So none of, and similarly for the top row, if she goes to the top row, she can't go essentially that way either, right? Because then she would be that would if that was on the path, it would equal the sum of the topmost, which is itself, plus another digit, which would then not be equal to itself. So that's impossible. So this D then is not passable because she would teleport instantly to this one. So she has to essentially go around this way somehow. So her path has to go from... Oh, we are on the edge only. So to get to the cupcake, she has to go this way. And then this way at least. She could potentially not be going that way, but we don't know. So she could continue here and then go down or just go whichever way, right? We also know this is on the path. So she enters each of these rows. So none of these rows can be 1 through 8. Sorry, none of these cells can be 9. If any of them are 9, then therefore her path would equal 9 plus another digit, which is impossible because the digit would be 1 then at least, and therefore that would equal 10, which is not a digit. Therefore, none of these could be 9. This cannot be 9 because we know she gets to the cupcake, and that's on the path. So that can't be 9 because that's the sum of this digit plus there. Where's the 9 then? It does have to be there. So that's a 9. So since that's 9, what's on her path then? This has to add up with at least 7 other digits to form another digit. Well, that's only 1 or 2 here, right? It can only add up with 1, 1 with 1, 1 with 2, 1 with 3, 1 with 4, all the way up to 8. But 2 could also fulfill that. But 3 cannot. 3 would have to be with 1, 2, 3, 4, and 5, 6. So it could only add up with 6 digits to form another digit. So this is only 1 or 2. Similarly, this is also only 1 or 2. 9 could be on there, and it could also not be. Well, let's say, okay. Let's say this was 2. This would obviously have to be 1. And the thing is, 2 can only add up with 1 through 7 to form another digit. So this would have to be 2. This would have to be 1 through 7, which would force this to be 8. Therefore, this would have to be 1 if that were the case. Right? If this were 1 and this were 2, this again would have to be 1 through 7 here, and this would be 8. Okay, well, anyways, we have a 1, 2, 1, 2 pair. Well, okay, this is 1 and 2, right? We know one of them's 1 and one of them's 2, so therefore this must be 3. The red current always sits between an even digit and an odd digit. So this is odd, which makes this have to be even. So this is 4, 6, or 8. This can never be 4, because if it's 4, this would have to be 1 and 3 here to add up to it. And that's not possible. So we know these are all on the path. Let's make it... I was thinking since we already have a green, we could make it pink. But I don't know if that's any better. So this cannot be 4. If this is 6, this could be 1 and 5 or 2 and 4. That works. If it's 8, so this is either 1, 5 or 2, 4. If this is 8, this could be 1, 6 or 2, sorry, 1, 7 or 2, 6. So either of those works. The A has to be specifically 4 through 8. This is 4 through 8. These are also 4 through 8. This can't be 4, because this is at minimum 4, so this would have to be at least 5. This can't be 8, because that would be 8 plus whatever, right? So we know 3 cannot be here. So, things could go this way, or potentially could go this way. Um, hmm. Oh, these two, one of these is odd and one of them is even. Well, this is the sum of these two numbers. So to be different, a different parity than this one specifically must add with an odd number to change the parity. Therefore, we know this is 1 and this has to be 2 then. The 2 can only add up with 7 other digits to form actual valid digits. So therefore, this has to be an 8, and the rest is 2 through 7. Therefore, this has to be 3 through 9, and therefore this must be a 1. And therefore, it can things cannot go here because that's not the sum of 8 and 2. So she has to go down here. This is 4 through 9. And these obviously cannot be 8. So since these can't be 8, that means these can't be 6, because they would then add up to 8 with the 2, right? Let's see. So 1 cannot be any of these. 1 has to be one of these 3. We don't know what this is. So these are different parities. Finks could actually go down here. Oh, this can't be 1. So therefore, this can never be 8. So therefore, this can't be 8. We know the 8 has to be one of these cells, which means 9 has to be correspondingly be one of those cells. So this could be, this can't be 2. It could be 3 at least. 3, 4, 5, 6, 7, which means this has to add up to at least 5. So this is 5, 6, 7, 8, and 9. And we know that's on the path again. If she goes here, the problem is that this would have to be at least 8 plus 4, which is 12. So she cannot go here. She could go here, in which case she teleports there. Ah, well, okay, so she can never enter here, because then she would teleport to here. So this is blocked off. If she teleports to here, right? The problem is she would then enter here. I guess she could teleport back here. That's fun, I guess. So if she enters here, she could teleport here. But can she ever enter here and go this way? Or go enter here and go that way? Or go this way, essentially? I don't think so, right? So if she enters B, she could go that way, and then the problem is this would have to be 8 in some number to add up to a digit, which would be 8 and 1. But then she could not go any of these ways, right? So she can never essentially she could either enter in A here, which would teleport her there, or she could enter B here, which would teleport her to here, which would teleport her to A, right? Because she can never go this way and then go extend here. She can't go to E because it would teleport her there. Therefore, all of these spaces are ruled out. She has to go to A somehow. So this is always on the cell, on the path. So she always goes here. So this has to be the sum of, ooh, that's not good. How is this the sum of 2 digits? It would be 4 and 5 at least. But 9 is already here. Huh, that's a problem. Hmm. Question. So then is this not 9 here? Whoops. Whoops. Sorry. Is this not 9? I don't see how it could not be 9, right? This can't be 9 because none of these can be 9 because they need to add with this with another digit to basically form to add to another digit. This obviously is on the set, so this cannot be 9. So this one has to be 9. But then we run into this problem essentially. Okay, this can't be 5 or 7 because it's 4 or 6 to add up to 6 or 8. So either way, 6 has to be here, which means none of these can be 6. This is either, oops, this is either 2 and 4 adding up to 6 or 2 and 6 adding up to 8. I think you have to teleport, though. That's the problem. Hmm. Oh, wait, hold up. This is a 2 by... Okay, yeah, you can okay, so this is not enterable. Yes, okay. So this is... Yeah, okay. Right. This is not enterable because specifically it would have to equal 4 plus 5 at minimum if it were on the path. So this is not on the path. This is not on the path. I forgot about the diagonal movement. That's the reason why. So it cannot. Finks cannot enter here. She can't go diagonal here. She couldn't go diagonal here either because of the similar problem because that would add up to 12. So she has to go this way. She can't go diagonal here. She can't go diagonal here because that adds up to 10 if that were on the path. Therefore, she must enter here and then must enter B, right? Which instantly teleports her to this B. But I forgot she can go diagonally. So she can go here and then she can go here. And that's what she has to do, right? She can only enter in one area in this column because this has an 8 on top. Therefore, this would be D has to be a 1 to add up to 9. And then she has to exit back out that way. So she enters here. B can never be 1, so this can't be 1 then. She enters here, and then here. So she cannot enter any of these. She cannot enter remaining any of these, right? So why can't she just go straight down? I'm suspecting that she's not going to be going straight down. Anyways. So this is 3 through 8. This is 3 through 8. This must be 4 through 9 then. So this digit must be at least 6, right? So, because it's at least 2 and 4 added together. So this is 6, 7, 8, 9. But this has to be the same digit, and it cannot be 9. So this can't be 9, this can't be 9. This is 6, 7, or 8. Because of that, this cannot be 6 or 7. Also, we know that this has to be... One of these has to be 6. So none of these can be 6. Okay, so this can never be 9. I don't know how I got a 9 there. If this is 6, it's 2 here and 4 here, right? But the problem, I guess this could be 3 and 3. That could be the case. If this is 7, so this can never, okay, so this can never be 5, 6, or 7. If this is, yeah, if this is 5, 6, or 7, that would be with 4, which adds to up something greater than 8. This can't be 7 either, because if this is 7, this would have to be 7 and 2 at minimum, which would add up to 9. we know 7 has to be one of these two because it cannot be these two, because 7 with a 2 adds up to 9, or 7 with a 5, 2 and 5 add up to 7, but this has to be even. So 7 has to be one of these two, so this can never be 7. So this is either 6 and 8. This is 6 or 8, essentially, right? So since this is 6 or 8, this can't be 7 here. And this can't be 7 or 8 here. Because it has to add up to 6 or 8 here. So either this is 2 and 4, it's 4 and 4, or it's... Okay, so if this is 2 and 4, that would mean this is 6 and 8, and that works. So this would be 6, and this would be a 5-7 pair. Wait, so this is 4 with 1. Okay, well, there we go. This has to be some digit with 1 to add up to another digit. Well, it can only be 4, 1, and 5, because 5, 1, and adds up to 6. And 6 can't be here because we know one of these is 6, because this is odd and this has to be even, which makes that have to be even since this is even. So this can only be 4 and 5 to add up there. So this can't be 4. This must be 6, which makes that 8 to add up to 2 and 6. This is not on the path. So this is the remaining 7. So therefore, this is 7. This cannot be 7 then. None of these can be 8. None of these can be 6. This has to be specifically 2 or 4 to be with 6 or 8 to add up to 6 or 8. None of these can be 4, and these can't be 4. This can't be 5 anymore. This can't be 7. Huh. This plus, so this is equal to the sum of this plus this number, right? This is equal to the sum of this plus this. So this can never be 7 here. This can never be 7 here. So that would be 4 plus 3. So this can never be 3. Therefore, we have a 2, 4, 5 triplet in row 1. And this has to be 6, 8, and 9 here. Right? But these can't be 8. Therefore, this cannot be 4. Where they have a 6, 9, 6, 9 pair in row 3. Therefore, this must be an 8. And this must be 8. And that eliminates 6 and 9 from the rest of the box, too. So this can't be 6 or 9. This can't be 5 anymore for the rest of the box. It's because we have a 2, 5, 2, 5 pair, and this must be 4. So again, this can't be 2, 4, or 5. This must be 3 or 7. So 7, we have a 3, 7, 3, 7 pair in box 2, which eliminates 3 and 7 from the rest of the box, and 4 and 7 are eliminated from the rest of the box. Therefore, we now have a 5, 6, 9 triplet in row 2, which eliminates 5, 6, or 9 from the rest of row 2. So therefore, this can't be 5. This must be 4, which means this is the sum of 2 and 2. This cannot be 4 or 5. This must be 7, which makes that a 5. And the last digit here must be 3. Therefore, these are both 1 and 2. They cannot be on the path because they are never the sum of 3 plus, or at the minimum, or plus 4. So these are never on the path. This is on the path. This is on the path. This is on the path. This cannot be 8. And this has to be 2 plus something. So it's either, if it's 2 and 3, this is 5. If it's 2 and 7, it's 9, but it can never be 6, 2, and 4 because we already have a 4 here. Therefore, this becomes specifically 3 or 7. This has to be then 3 or 7, but it can't be 7 because we already have a 7 in box 6, so this is 3, which forces this red to be 3. And we celebrate because 3 is in the corner. We celebrate because we now know this is 2 plus 3 for this cell, so this must be 5. This can no longer be 3. These can't be 3. So this can't be 8 here. I don't know why I deleted that. This can't be 8. This can't be 7. This can no longer be 4, because if that's 4, this would have to be 3 to add up to that. We know 7 has to be one of these two cells. Because 7 is one of those two cells, that means 8 must be one of these two cells because it must add up with 1 to form an 8. So 8 has to be one of these two cells, which eliminates 8 from the rest of box 7. So therefore, this can no longer be 8. Now we have a 5, 6, 7 triplet in column 1, which eliminates 5, 6, and 7 from the rest of the column. Therefore, this must be an 8, which forces this to be 9. So this cannot be 9. None of these can be 9. So this can't be 9 either. This has to be 6, 7, or 8. This is also 6, 7, or 8. This must be 1 and 1 add together, so this is 2. This has to be 6 or 7 to add up with these digits. Therefore, this is a 4, but it could be on the path, because 4 is a sum of 3 and 1. Now, where is the 7 in? We know 7 can't be in this cell, because we know one of these two cells has to be 7. Because this can't be 7 and this can't be 7. Therefore, this is 7, which makes this a 6, 8 pair in column 2, which eliminates 6 and 8 from the rest of the column. Therefore, this must be 7, which means this has to be 6 to add up to, with 1 to add up to 7. The remaining digits are 3, 4, and 5, and this can't be 3. None of these can be on the path because they are not the sum of the topmost and the leftmost compared to its cells. This can't be 6, so this is 5, 7, 5, 7. We have 6, 8 here. This has to be 1, 2, or 9. This can never be part of the path. This could be... so this has to be 6 plus 3 if it's part of the path. But we know Finks needs to go either here or here. So one of these two needs to be part of the path. This can't be, so Finks does have to go this way. So she does go around here. Which means all of these are part of the path. 4 works because of 1. Therefore, this must be 9 to be... I add up to 3 and 6. These can't be 9. This must be 3 plus 3, because we only have the choices between 3 and 7. So this is 3 and 3, which makes that a 6. This has to be a 7 then, which means this is 3 plus 2 here. This is 5. 2 plus 7 is 9, and 4 plus 2 is 6. This is 5 plus 4, so this must be 9, and this is 2 plus 4, so this must be 6. We know this is a sum of these two digits, and 3 and 7 doesn't work, so this must be 3 plus 5, which makes this 8. This can't be 8, so this is 6, which makes this 8, and 7. That does work. This must be the sum of 2 and 7, so it's 9. But now we have a 1 here, and again, her path cannot go to a 1. So this is not on the path. She could go to any of these 3 cells. We're not sure which. This can't be 1 anymore, so that must be 2, which makes that 1. D is a 1, so this is also a 1, which means this can't be 1, so this is 2, this is 1. C is the same digit. Well, cannot be 1, cannot be 2, cannot be 3, because that C's there. Cannot be 4, cannot be 5, cannot be 6, cannot be 7 because it sees it there, and cannot be 8. Therefore, the C has to be a 9. So this is a 9. She could enter there because she can teleport. That 9 equals the sum of 3 and 6 and equals the sum of 4 and 5. So she could enter either of these teleportation areas. What are remaining cells? This has to be 3, 4, and 7. Is that right? Yeah, 3, 4. This can't be 7. This could be 3, 4. It can't be 7. So this must be a 7. 3 and 4 can never be the sum of 5 plus 5 and cannot be sum of 5 plus 7. So these cannot be on the path. Because of that, we know that she has to enter this digit. She cannot enter in, she cannot cross this way. All of these are blocked. Therefore, she must continuously go here. So she must go from here to the cupcake. And therefore teleports from this area. And they both fit, so they're both 9. This Mao must be the sum, so this has to be 7, which is 3 plus 4. This is 3 plus 5, therefore this is 8, which makes this a 2. These are all along the path. She could go here, or she could go here. If she goes here, that would be 12 for the path. So this is not possible to be the path. Okay, yeah, where are the possible path ones? This can't be, this can't be, this can't be. 4 and 8 cannot be, 4 and 6 cannot be. 4 and 1 could be, 4 and 11 cannot be. 7 and 8 can't be, 7 and 6 can't be. 7 and 7 can't be, obviously. 8 and 3 can't be. 9 obviously could be. This could be. And 3 and 7 cannot be. So she has to go specifically at least this way. So she connects here. And we don't know whether she connects this or this. So these are all on the path. They have to be. So then we have, specifically, we know what they are. So it has to be 6, 5, and 8. This can't be 5, so this is 4, which means this can never be 4. This has to be 7, but 7 is not the sum of 1 and 3. Therefore, this cannot be the path. So she has to go this way to teleport here. This is not on the path. Okay, now we just have to do normal Sudoku. So this can't be 4. What's left here? This is 2 and what? 4. So this is 2 and 4, this is 2 and 4. These have to be, okay, so one of these has to be even because we have one even and one odd between those courants. The only even possible now in column 6 is 2. So this has to be a 2, which means this cannot be 2. So this is 4, which makes that a 2. 2 has to be with an odd, and it can be with 1 or 3. So this is 1 or 3, this is 1 or 3, but it can't be 1, so therefore this must be 3, which means this can't be 3. This has to be 1 or 2. And we're left with 3 and 6. This can no longer be 6, so this must be 3, which makes that a 6. This is an odd, so it must be next to an even for the black courant, or red courant. So this must be 2, this is 1. And now we're just doing Sudoku. This can't be 3, this must be 4, which makes that 3. The 2 cannot be here, so this must be 2. This can't be 3, so this is 5. This is 3, this has to be 5. We're missing 1 and 4 here. This can't be 1, so this is 4, which makes that 1. This must be a 6. This must be a 4, and this has to be a 5. And that's the puzzle. Cells visited, 31. Test date, December 23rd, 1974. Cells visited, 31. Red courants eaten, 1. Teleports used, 2. Despite having had over 2 months off, Finks got straight back into test mode. picking up right where she left off, as we'd hope. Frustratingly, despite weeks of tinkering with the teleports and thinking the issues were fixed, Teleport B once again overheated after Finks had entered it. Why is it just that one that's being temperamental? Further investigation required. Anyways, very cool puzzle. Interesting rule set, actually, which leads to certain constraints. Um, yeah. Again, I love the whole Rat Run series is very cool. And again, this doesn't disappoint. It's a very cool logic behind it. The idea, the theme fits very well. Yeah. And anyways, I hope you enjoyed this run of Rat Run, and I'll see you next time on Frank Puzzles. Take care.